So in this video, we'll do a bunch of double integrals. And let's just start right away. Evaluate the double integral from 0 to 1 and from 0 to square root of 1 minus y squared, x squared plus y squared to the power of 10 dx dy. Okay, so the idea in this exercise is to get used to evaluating these double integrals, and that usually is being done by converting from Cartesian to polar coordinates, or just changing the order of integration. Well, what is the hint? The hint is that whether you recognize whether the boundary is a region that can be easily described in polar coordinates, and also whether the integrand can be expressed in as a nice function, or can be easily expressed uh, through polar coordinates. Okay, well, we should be aware by now that x squared plus y squared in polar coordinates is just r squared. So the integrand becomes just becomes r squared to the power of 10. Okay, then let us just see what the bounds are going to represent, what region these bounds are going to represent. Well, x is between 0 and square root of 1 minus y squared. Okay, and this is x is equal to square root of 1 minus y squared is just a semicircle, okay, to the right of the y-axis. Okay, so multiply both sides, you have square both sides, you have x squared is equal to 1 minus y squared. X squared plus y squared is the equation of the unit circle. Okay, but here, because as x is positive square root of 1 minus y squared, that means only the positive values of x, so only this semicircle. So that's given only by the first bound. But then y says only go from 0 to 1, so y gets also only positive values, so we're just restricted only to the first quadrant. Okay, this is the region where we integrate. Well, this region here is expressed in polar coordinates. That means that theta is going to go from 0 to pi over 2, and r, obviously, we're talking about the unit circle from 0 to 1. Okay, so these are the bounds of the same integral expressed in polar coordinates. So that becomes the integral from 0 to 1 dr from 0 to pi over 2 d theta. Now, don't forget, when we change this to polar coordinates, I need to multiply this by r, and then the integrand x squared plus y squared is just r squared, so that's r squared to the power of 10. And these are independent, so you can just write here from 0 to pi over 2 the theta times the interval from 0 to 1 r to power 21, right? R2 to the power of 10 is r to the power 20 times r, that's r to the power 21 dr. This integral is easy, that's only pi over 2 times 1 over 22 r to power 22 from 0 to 1. And that's finally, the answer is pi over 44. Okay? Oh, it is a good idea from now on, the moment when I write down the problem, that you guys just pause the video and solve it by yourself, and then come back and check the solution, check whether it was right or wrong. Okay. The second problem is evaluate the double integral over the region R of x squared dx dy, where R is consisted of all the points x, y, such that x squared plus y squared is greater than 1, less than 4. Moreover, x is greater or equal to 0, y is greater or equal to 0, and x is greater or equal to y. Okay, so let's see what this region actually represents here. First of all, x squared plus y squared is equal to 1 is the unit circle. Right, so this is x squared plus y squared is equal to 1. If x squared plus y squared is greater than 1, that we are talking about all the points outside of the unit circle. Okay? X squared plus y squared is equal to 4. That's a circle of radius 2, right? The circle outside is x squared plus y squared is equal to 2. Okay? And then if x squared plus y squared is less than 4, that means we are talking about the points in this washer, let's call it that way. Okay. Now let's concentrate on the next boundaries. X is greater than 0 and y is greater than 0. That leaves us only with the first quadrant. Okay, and finally x is greater than y. Well, let's just sketch the line x is equal to y, and on what region x is greater than y? Well, that's to the left of this line. So basically, we're only talking about this region right here. Okay, so if we zoom that in a little bit, we're just integrating over here. Okay. Well, this is the line x is equal to y, which implies right away that theta runs between 0 and pi over 4, and r is evident that goes from 1 to 2. Okay, then our integral can be written as double integral from 0 to pi over 4 d theta, integral from 1 to 2 dr times r, and then what is x squared? Well, x squared, x is equal to r cosine theta, so x squared is going to be r times cosine theta squared, or r squared cosine squared theta. Okay. This is an easy integral to evaluate, and you should get at the end 15 pi plus 2 over 32. This should be the answer, unless I made some mistakes. Problem number 3, the double integral going from 0 to 1 and from 1 minus y to power 1 quarter to 1 sine of x to the power 5 dx dy. Okay, so here we don't have here this here doesn't represent a friendly region that can be friendly described in polar coordinates, right? Neither the integrand suggests that polar coordinates will be helpful. So what is the other idea that we have in mind? That is changing the order of integration and hoping that that will help us, okay? So first of all, I have that x is bounded between fourth root of 1 minus y and greater or equal to 1. So let's deal with that, this inequality, this set of inequalities here first, and then figure out where that's going to lead us, okay? So how to sketch the first one? That's the fourth root of 1 minus y is equal to x. Well, if you're not comfortable with this, then raise this to the power of 4. Both sides, you have 1 minus y is equal to x to the power of 4. Or simply 1 minus x to the power of 4 is equal to y. Now this function should be easy for you to sketch, in a sense that x to the power of 4 will have the same shape as the quadratic, right? And then negative x to the power of 4 is just going to be inverted parabola. This is the negative x to the power of 4 plus 1. We have this right here. So this is 1 minus x to the power of 4 is equal to y. Now, be careful here. It says that x is greater than, or sorry, x is equal to positive square root of 1 minus y squared. So that means that we are talking only about this part of the curve only. Of course, this point here is going to be 1. What does it mean x to be greater than this root, right? Well, you can check. Let's check the point 0, 2, 0, right? Let's check the point 2, 0 whether it satisfies this. Well, is 2 greater than 4th root of 1 because y would be 0? Yes, so that means that that inequality gives us this region right here. Okay, but then it says x is less than 1 and x is equal to 1 is just this line here, x is equal to 1. So if x is less than 1, that means we're talking about this region right here. So intersection is the intersection that we talk about. Okay, so far I have only this part here expressed by this inequality, these two inequalities, right? Because y is equal to 1 minus x to the power of 4, obviously this point here is 1, and this line is y is equal to 1. So now if you look at the second boundary that says y is between 0 and 1, obviously we're talking only about this small part right here. Okay, that is the region above which we integrate. So let's just zoom that in a little bit. This is where we integrate. Okay, that's what we were talking about. This is the function x is equal to the 4th root of 1 minus y. Okay, this is the line y is equal to 1. This is the line x is equal to 1. So now I want to change the order of integration. I want to write y that is bounded between functions of y. Okay, so y goes from this curve here, expressed in x, that's 1 minus x to the power of 4, and it's less than, obviously, the upper boundary, that's 1. In that case, x is just going to go from 0 to 1. So this integral here, if I continue here, right, by changing the order of integration, x is gonna go from 0 to 1 dx. Y is gonna go from 1 minus x to the power 4 to 1 dy, and here I have sine of x to the power of 5. Now I integrate first with respect to y. That means this function doesn't depend on y, so I treat it as a constant. Okay, so that's going to be equal to definite integral from 0 to 1 sine of x to the power of 5 times y, right? The integral of dy is y, 1 minus x to the power of 4 to y dx. Now I simplify this expression right here. Integral from 0 to 1 sine of x to the power of 5 times 1 minus x to the power of 4 dx, and this leads me to the expression sine of x to the power of 5 times x to the power of 4 dx. And now this is going to be an easy example to solve. You just need to use the substitution rule here. X to the power of 5 is equal to u. And then this is a very, very, very elementary Cal 2 integral that should lead you to 1 minus cosine of 1 over 2 as an answer. Okay, so please check that and let me know if you got that result. Okay, and for the rest of the problems, for the rest of the session, we'll have problems like this where you have to recognize whether it's easier to switch to polar or polar coordinates or change the order of the integration. So now the double integral from -1 to 0 and from 0 to square root of 1 minus y squared. So far, at this very moment, you should recognize that we are talking about, this is going to be a semicircle right here, right? Square root of 1 minus y squared. So maybe in our mind, we already have the polar coordinate, okay? And then we have e to the power square root of x squared plus y squared over square root of x squared plus y squared dx dy. Okay, so let us see here, x is between 0 and square root of 1 minus y squared. We already worked with this inequality. X is less than square root of 1 minus y squared in one of the previous examples, and that was just the semicircle to the right of the y-axis. Okay, that means x is greater than 0 and less than this curve, and now y is between -1 and 0, so that means we're just talking about this quarter of a circle. Okay, now theta, how to describe this this quarter circle. That means that theta goes from -π/2 to 0, and obviously r goes from 0 to 1 is the unit circle. Here x squared plus y squared is just equal to r squared, so that means that I'll have e to square root of x squared plus y squared becomes, now I'm just doing the integrand, is e to the power square root of r squared, which is e to the power of r, and in the denominator I'll just get r. So this is equal to the double integral from -π/2 to 0 d theta from 0 to 1 dr times r, the Jacobian, be careful. And here I have e to the power r over r. Well, these two are gone. And this integral now is very simple, right? The double integral of e to the power r dr d theta is equal to theta evaluated from -π/2 to 0 times e to the power r evaluated from 0 to 1. That's 0 minus -π/2 times e to the power 1 minus e to the power 0. So the final answer should be e minus 1 over 2 times pi. Okay. Number 5, the double integral from 0 to 1 and from 0 to arc cosine of y, 1 over cosine of x dx dy. Okay, again, I'm going to remind you, it's a good idea to pause this video right now and try to solve this integral by yourself first. And then if you get stuck, play the video then, or if you are finished, check the answers with my solution, okay? Here again, nothing suggests the polar coordinates, so we're trying to see whether the changing the order of integration will help us, okay? So x is between 0 and arc cosine of y, and then arc cosine of y looks like this, and this is from -π/2 to pi/2 at 0. Our cosine of 0 is 1. Okay. So when x goes from 0 to arc cosine of y, sorry, x is less than arc cosine of y. Sorry about that. This is wrong. So this will look like this, right? If x is equal to arc cosine of y, that means that cosine of y is equal to sorry, cosine of x, okay, finally got it. Cosine of x is equal to y, so cosine of x, this, okay. So basically we're talking about this part of the graph, okay. So x is between 0 and arc cosine of y, and y is between 0 and 1 right here, okay. So how to describe this? How to describe this by changing the coordinates? Well, obviously from here, y is going to be less than 0, sorry, greater than 0 and less than cosine of x, and then x is going to be between 0 and pi over 2. So this becomes the interval from 0 to pi over 2 dx, and the interval from 0 to cosine of x, 1 over cosine of x dy. Well, that's the interval from 0 to pi over 2. I'll integrate first with respect to y. That means I treat the second function as a constant. So 1 over cosine of x times y integrated from 0 to cosine of x dx. That's equal to the interval of 1 over cosine of x times cosine of x minus 0 dx. And obviously these two terms cancel each other out. I have the interval of dx, which is just x, evaluated from 0 to pi over 2. That's simply pi over 2. Okay, so problem 6. A double interval from a 0, similar interval from 0 to 1, arc sine of y to pi over 2. Here I have xy over sine of x dx dy. Okay. In order to evaluate this, I'll have x times cosecant of x. And in order to solve that, if possible, I have to use integration by parts. So is there an easier way to do this? Well, nothing suggests here using polar coordinates, then let's just try. Let's just try changing the order of integration. So x is greater or equal to arc sine of y, and it's less than pi over 2. Okay. Again, one way we can sketch this is that I express the arc sine of y function that is equal to x as y is equal to sine of x. Okay, so that's pi over 2, okay? And then x is greater than arc sine of y, but less than pi over 2. So obviously we're talking about this region. Sine of pi over 2 is 1, and then y is from 0 to 1. Okay, but from this graph right away, changing the order of integration here should be evident. Okay, so here y would go from 0, and its upper bound is going to be this curve. Well, this curve in terms of x is sine of x, and then x is going to be bounded between 0 and pi over 2. Right? X goes from 0 to pi over 2. So this would be x goes from 0 to pi over 2 dx. Y goes from 0 to sine of x. Then here I have xy over sine of x. And then I first integrate with respect to y. Okay, when I integrate with respect to y first, I treat x over sine of x as a constant. times 1/2 y squared from 0 to sine of x dx. This will be equal to interval from 0 to pi over 2 x over sine of x times 1/2 sine squared x minus 0 dx. Cancel these two, and then I have just a integration by parts from 0 to pi over 2, which will be what u is equal to x, du is equal to dx, dv is equal to sine of x, v is equal to negative cosine of x. So integration by parts gives us negative x cosine of x evaluated from 0 to pi over 2 minus the interval of negative cosine of x, so that's plus interval of cosine of x dx from 0 to pi over 2. That's 1/2 negative pi over 2 times cosine of pi over 2, which is 0, minus 0 times cosine of 0. Okay. Plus interval of cosine of x is sine of x evaluated from 0 to pi over 2. So as I said, pi over 2 is 0, which makes this whole thing 0. 0 times cosine of 0, which is 1, is 0. Finally, I have sine of pi over 2, which is 1. 1/2 times 1 is equal to 1/2. So let's do this interesting integral here. Integral from 0 to 1 and e to power y to e 1 over ln of x dx dy. Now, if there is anyone interested in mathematics, moreover interested in number theory, right? Maybe you guys will know this function here, which is called the logarithmic integral, defined as the interval from 0 to 1 over x, 1 over ln of t dt, okay? And in the number theory, it's very important because the function pi over x gives us the number of primes smaller, oops, sorry, less than x. Okay, for example, pi of 6 tells you how many primes are there less than 6. So how much is that? 2, 3, and 5. So this would be pi of 6 is 3, right? Or pi of 9 would be 2, 3, 5, and 7. So this is equal to 7. Of course, we want to, when these numbers become very big, it's very difficult to figure out whether a number is prime or not. You will learn about this in number theory if you take number theory. And it was Gauss who proposed that pi over x is more or less equal to the logarithmic integral, right? It's about the logarithmic integral. Now we know that this is the bound of pi x 1.1 times, okay. Now what is the thing is that this antiderivative in elementary terms doesn't exist. Elementary antiderivative doesn't exist. So in that sense, this one is very interesting, okay? Although we're not talking about double integral here, still it feels good that we are able to solve this integral without using any either approximation or any any software, okay? So again, I'm going to try to change the order of integration where x is between e to the power of y and e, okay? So this is the curve y is equal to ln of x, or x is equal to e to the power of y. Okay, so this is the number 1, and here is the constant e, right? So if x is to the right of this curve, but to the left of this number, this is what I have. And then how much is this number here? Well, that's ln of e. Ln of e is 1. Okay, and indeed y goes from 0 to 1. So if you change the order of integration here, now I want to bound y, so y will go from 0 all the way to this curve, right? Its ceiling is this curve, so y will go from 0 to a function expressed in x, and then x will go, as we can see from the graph, from 1 to e. Now our integral becomes from 1 to e dx, from 0 to ln of x dy, 1 over ln of x. And now this is very, very simple. I integrate first with respect to y, so I keep 1 over ln of x as a constant, times y from 0 to ln of x dx, which is the integral from 1 to e, 1 over ln of x times ln of x dx. These two are cancelled. Integral of dx is just x evaluated from at the boundary from 1 to e. The answer is e minus 1. Problem 8. So we're evaluating the integral sine of pi square root of x squared plus y squared over square root of x squared plus y squared dx dy, where r is the region where x squared plus y squared is less than 1 and x is greater or equal to 0. Okay, so what is this region? Wow, this region is like this. Okay, and for the third time the same region comes back, so I should have maybe used some different examples. Here theta is between negative pi over 2 and pi over 2, and r is between 0 and 1. The integrand, right, square root of x squared plus y squared in polar coordinates is r squared, which gives me just r. So I have r here and here. So when I'm changing this to polar coordinates, I get, so first I integrate from negative pi over 2 to pi over 2 d theta, from 0 to 1 dr times the Jacobian r times the function expressed in polar coordinates, that's sine of pi times r over r. Well, r and r cancel out, and I have the integral from negative pi over 2 to pi over 2, the integral from 0 to 1, sine of pi r dr d theta. These integrals are independent, so right away I can evaluate the integral d theta, so it's from negative pi over 2 to pi over 2. Integral of sine of pr is cosine of pr over sorry, pi r over pi evaluated from 0 to 1. And here I get pi over 2 minus negative pi over 2 with just pi, right? Here I get the cosine of pi minus cosine of 0 over pi. Which is, I'm sorry, I made a mistake. The integral of sine is a negative cosine. Okay, so about that. Okay, so I have times negative this. Okay, so pi over 2 minus pi over 2, that's pi over 2 plus pi over 2 is just pi. And that pi cancels with this pi. Here I have negative cosine of pi is negative 1 minus cosine of 0 is 1. So the answer is 2. And we have 2 more problems. One being okay. So set up the double integral. In Cartesian coordinates. If it says set up, then we don't have to evaluate it. So and the integral is from 0 to pi over 2 and from 0 to 2 cosine theta r cubed sine of 2 theta dr d theta. Okay, so let's first deal with the bounds. Okay, what do we have here? R is bounded between 0 and 2 times cosine theta. Okay, so how is this going to look in the xy plane? Okay, so r is greater than 0, that's fine. I want to sketch r is equal to 2 cosine theta. Oh, just give me a second. Okay. Well, what is this, right? So how do we sketch this? Well, when you have in theta and r, right? So 1, 2, 3, 4, r is greater than 0. Okay, so this is pi over 2. So this is 2. Here I have this negative 2. And this curve continues, right? This is just r is equal to 2 times cosine theta, right? But then it says that theta is just between 0 and pi over 2. So we're just talking about this region right here. Okay. If I'm about to sketch this function in the xy plane, what am I going to get? Well, when theta is 0, the radius is 2. Okay. As theta goes towards pi over 2, so as theta goes towards pi over 2, the radius diminishes to 0. and then it completes the circle when we're talking about pi over 2, right? But because, when theta goes all the way to pi, right? So this circle is completed from 0 to pi. We've talked about this. But because theta goes only to pi over 2, we're just talking about this semicircle, okay? So what is the equation of this semicircle? Well, let's find the equation of the circle, and then we'll figure out what is the equation of the semicircle only. So here I have, it's a circle with with center at 1, 0. So that means x minus 1 squared plus y minus 0 squared is equal to, and the radius is obviously 1. Okay. So how am I going to describe this semicircle? Well, here I can see that all the y values are positive, so let's express y in terms of x. Y squared is equal to 1 minus x minus 1 squared. And then y is equal to square root of 1 minus x minus 1 squared. So here I should have plus or minus, but because we're talking about the upper semicircle, this is just positive square root of this. Or if you drop the parentheses, if you drop the parentheses, yes, within the root, you get that y is equal to square root of 2x minus x squared. Okay, so the bound of y is between 0 and square root of 2x minus x squared. Okay, and x obviously goes from 0 to 2. X goes from 0 to 2. So I have found the bounds of the double integral in Cartesian coordinates. Now let's deal with the integrand. The first thing that I have to notice is that this Jacobian here is not explicitly written, which is fine. But let's do that in order to be aware of what's going on. So here I need some r d theta. I'm going to borrow that r from here, which is going to leave me with r squared sine of 2 theta from 0 to pi over 2, from 0 to 2 cosine theta. At this point, I know what the bounds of the double integral in Cartesian coordinates is going to be. Now I'm just wondering what the integrand is going to be. Okay, so this is equal to, and here I'm going to express the integrand, which is simply r squared sine of 2 theta. Well, sine of 2 theta is 2 sine theta cosine theta. And now it should be slightly easier to recognize this. So this is 2r squared sine theta cosine theta. That can be also written as 2r sine theta times r cosine theta, or 2y times x, right? Where this is y and this is x. And now I have everything. I have the new bounds are from 0 to 2. Dx, y goes from 0 to square root of 2x minus x squared. And the integrand, so dy, and the integrand is 2y or 2xy is the same thing. And the last problem is evaluate the integral from negative pi over 4 to pi over 4 from 0 to 3 secant theta. Again, be careful, r cubed sine square theta dr d theta by changing it to Cartesian coordinates. Okay. So let's first work with the bounds, then with the integrand, and at the end we solve it, okay? So theta goes between negative pi over 4 and pi over 4, and r goes between 0 and 3 times secant theta. So this one is going to be easier one to think about, right? In xy plane, this is negative pi over 4 and just goes to pi over 4, or from the line x is equal to, sorry, y is equal to negative x to the line y is equal to x, okay? But what will happen with this guy? Okay, so r greater than 0, it's fine. How does this look like? R is equal to 3 secant theta. Well, divide both sides by secant, you get r over secant theta is equal to 3. 1 over secant is nothing else but cosine, so I get r times cosine theta is equal to 3, right? 1 over secant is cosine. But r cosine theta is nothing else but x, so x is equal to 3. So now let's incorporate all of these, okay, and get theta is equal to pi over 4. That gives me the line y is equal to x. Theta is equal to negative pi over 4, right? Negative pi over 4 and pi over 4. And this line is y is equal to negative x. And finally here, x is equal to 3. Okay, so this here is the region above which we integrate. Okay, so how this region is going to be represented in Cartesian coordinates? Here, x goes from 0 to 3, and y obviously goes from the line negative x to the line positive x, right? Y goes from here for each different x. Y is above the line negative x and below the line x. Okay, and at the end we need to deal with the integrand. So this is the double integral, still in polar coordinates, r squared sine square theta times the Jacobian r dr d theta. Similarly, like in the previous example, I borrowed one factor of r. Okay, now we're ready to switch this into Cartesian coordinates. X goes from 0 to 3 dx, y goes from negative x to x dy. Okay, r squared times sine squared is r times sine theta squared, and r times sine is y squared. And now this is a simple integral to evaluate. Integral from 0 to 3, integral of y squared is 1 over 3 y cubed, evaluated from negative x to x dx. That's equal to 1/3 times the integral of x to the power of 3 minus negative x to the power of 3 dx. From 0 to 3, that's 1/3 negative times, this is negative 1 to the power of 3, that's negative 1, so negative times negative becomes positive, and this is 2 times x cubed dx from 0 to 3, which is 2/3 times x to the power of 4 over 4, where x is evaluated from 0 to 3. And that is how much? 2 times 81 right? 3 to the power 4 over 3 times 4. And if you simplify everything, 2 cancels with 4, 81 cancels with 3, I get 27 over 2. Thank you very much. That was it for this video.